Have you ever held an ordinary iron nail in the palm of your hand? It feels solid, unremarkable, entirely grounded in our everyday world. Yet, that very same iron is the ultimate dead end for a giant star. It is the cosmic ash that spells the doom of giants. How does a blazing sun, millions of times larger than the Earth, suddenly fall into itself and leave nothing but a black hole behind? Let us start with the simple nail in your hand and end at the absolute edge of nothing. Turn that iron nail in the light. The iron you see is the same element flowing through your blood right now. It is also the final chapter for a massive star. For millions of years, a star is a delicate balancing act between the crushing weight of its own gravity, pulling inward, and the fierce outward push of nuclear fire. But when the star's core turns entirely to iron, that fire runs out of fuel. Fusion can no longer pay the energy bill. With the heat gone, gravity finally wins the war it has been fighting since the star was born, and the entire colossal structure begins to fold inward. If we fast forward the life of a massive star, the pacing becomes terrifying. For millions of years, it peacefully fuses hydrogen into helium. Then, as the core shrinks and heats up, the pace accelerates. It burns helium to carbon over thousands of years, carbon to oxygen in centuries, oxygen to silicon in less than a year. Finally, it burns silicon to iron. That final sprint is wildly frantic. The silicon burning stage can rage for only a few hours to a single day. The star becomes an immense, glowing onion of burning shells, all feeding a rapidly growing, heavy iron heart that sits perfectly balanced on a knife edge. Why is iron the absolute stop sign of the universe? It comes down to a harsh rule of nature. Fusing lighter elements releases energy, which pushes outward and holds the star up. But heavier elements require energy to fuse. Iron is the tipping point. If you try to fuse iron, you do not gain energy, you lose it. The cosmic bank account is suddenly overdrawn. The core stops generating heat, and the immense internal pressure plummets. Suddenly, the star is like a massive circus tent with its center pole violently kicked away. The heavy canvas of a million Earths begins to sag. At first, a very strange quantum mechanical pressure fights back. The electrons packed tightly inside the core push violently outward against one another. This is called electron degeneracy pressure, which is simply a rule of physics that says electrons refuse to occupy the exact same space. But this microscopic defense only works up to a strict threshold known as the Chandrasekhar limit, which is roughly 1.4 times the mass of our Sun. Above that weight, there is simply nowhere left for the electrons to go. The seats run out, and the final structural support fails completely. As the core squeezes tighter and the temperature skyrockets, incredibly high energy light actually begins to break atomic nuclei apart. This means the very light of the core is knocking its own building blocks to pieces. At the exact same time, the extreme pressure forces electrons to be swallowed by protons. This unholy union creates neutrons and ghostly particles called neutrinos, draining even more energy from the core. In a fraction of a heartbeat, the core loses both its basic bricks and its scaffolding. The collapse accelerates beyond return. Then, the inner core simply lets go. It drops inward like a steel elevator with its cables cleanly severed. In a blinding flash, matter is falling inward at a massive fraction of the speed of light. The entire plunge of a structure larger than the Earth down to the size of a city takes less than 1 second. It is a quiet, brutal, and breathtaking moment. You are witnessing a sun falling into itself faster than anything you could possibly comprehend, driven by a gravity so pure and absolute, it bends the mind. But this catastrophic fall does not continue forever, at least not immediately. The collapsing material slams into nuclear density. It becomes as densely packed as the inside of an atomic nucleus. Hitting this state is like hitting a solid steel floor at light speed. The inner core stops dead and violently rebounds. That sudden, impossible stop launches a shock wave that surges back outward, much like a colossal hammer striking an anvil and sending a deafening physical ripple through the body of a bell. However, that first rebounding shock is simply not powerful enough to blow the star apart. It tries to push through millions of tons of incredibly dense, infalling material, and it begins to stall about 1 to 200 kilometers from the center. It is exactly like a massive ocean wave racing up a steep beach, losing its momentum and dissolving into thick, heavy foam. For a brief, agonizingly tense fraction of a second, the entire fate of the star hangs suspended in the dark. Then comes the invisible storm. A torrential flood of neutrinos bursts out of the newborn neutron core for about 10 long seconds. These tiny ghostly particles almost never interact with ordinary matter. But in this moment, there are so impossibly many of them that a small fraction of their energy is absorbed by the stalled shockwave, heating it back to life. Staggeringly, about 99% of the total gravitational energy of the collapsing star escapes invisibly as neutrinos. The blinding light of the supernova we eventually see in the sky is just the spare change left behind. Humanity actually caught this invisible storm once, just hours before we saw the light. In 1987, a blue supergiant in a neighboring galaxy collapsed. Deep underground tanks of purified water on Earth lit up with a handful of tiny flashes from 24 neutrinos over a span of 13 seconds. It was a silent alarm. Hours later, the night sky bloomed with the brilliant light of a new supernova. Those fleeting flashes in the dark water were humanity's first direct whisper from the dying heart of a star. If the flood of neutrinos successfully revives that stalled shock, the outer layers of the star are blasted away into the cosmos. The star becomes a supernova. For a few glorious weeks, a single dying star can outshine an entire galaxy of billions. But as you watch that brilliant spectacle, remember that the magnificent light show is powered only by a tiny sliver of the actual energy released. The true engine of destruction was the dark, silent wind of neutrinos that had already washed over the universe and passed right through you without leaving a trace. In the aftermath of the blast, the crushed core faces one of two profound endings. The first is a neutron star. If the surviving remnant stays within a certain weight window, roughly between 1.5 and 2 times the mass of our Sun, it stabilizes into a sphere only about 20 kilometers across. Imagine a star holding the mass of 2 entire suns, crammed into a space the size of a small city. The gravity at its surface is a staggering 100 billion times stronger than on Earth. It is a dense, humming crystal that can ring like a struck bell and beam brilliant radio pulses into the void. But the other ending occurs when the weight of the core simply keeps climbing. If enough material falls back down, pushing the core past what physicists call the Tolman Oppenheimer Volkoff limit, which is about 2 to 3 times the mass of the Sun, even the immense pressure of tightly packed neutrons utterly fails. Space-time has run out of physical tricks to hold matter up. The catastrophic fall resumes, and this time, nothing in the universe can stop it. A black hole is born. A newborn black hole creates a boundary called the event horizon. It is the absolute point of no return, where gravity is so intense that not even light can crawl out. The size of this boundary is startlingly simple to picture. For every single sun worth of mass, the horizon expands by roughly 3 kilometers. So a newly minted black hole made from 5 suns will have an event horizon about 15 kilometers wide. It is a region of complete darkness the size of a typical human city, holding the trapped gravity of multiple stars. Remarkably, human beings saw this apocalyptic event coming on paper decades before we ever saw it in space. In 1939, scientists J. Robert Oppenheimer and Hartland Snyder modeled a collapsing star using Einstein's rules of gravity. Their mathematics showed that once a core becomes compact enough, absolutely no physical force can halt the fall. To an observer watching from safely far away, time near the edge seems to freeze, and the star's light slowly fades to a deep red. But to the falling star itself, the trap simply closes, wiping it from the visible universe in real time. We usually expect a star's death to be a brilliant supernova, but the universe is full of quiet tragedies. Sometimes a massive star does not go out with a bang at all. It simply dims and vanishes. In one distant galaxy, a massive red supergiant star was watched by telescopes for years. Then, between 2009 and 2015, it just faded away. No vast explosion, no blinding flash. There was only a very soft, invisible infrared ember left behind in the cold. The most haunting explanation is a quiet collapse. The massive core slipped past the limit silently, and a black hole swallowed the star whole, pulling a sun out of the sky without a sound. To be completely fair, the mechanical engine under the hood of a collapsing star is still wonderfully messy. How exactly does that stalled shockwave restart? Neutrino heating plays a major part, but so does the star's frantic spin, violently twisting magnetic fields, and turbulent, churning flows of boiling plasma. The inside of a dying star is not a neat, perfect sphere. It wobbles, it swirls, it is chaotic. Today, supercomputers are still chasing the full three-dimensional picture of this event. Because in the end, not every massive star dies the exact same way. Because light is trapped or delayed, there is another cosmic messenger we are eagerly waiting to hear. A true core collapse involves so much mass moving so violently that it should send out ripples in the very fabric of space-time, known as gravitational waves. We have not yet caught a clear, undeniable wave from a nearby, ordinary supernova. The signals are incredibly faint and complex. But one day when a close stellar collapse finally rings our vast detectors here on Earth, those invisible ripples will sketch the absolute inside story of the fall. This brings us to the strangest, most mind-bending implication of all. A black hole is not an object that has been added to the sky. It is a volume that has been subtracted from it. The mass of the dead star has folded the map of space so tightly around itself that the concept of direction breaks down. Inside that 15-kilometer boundary, all paths point inward. There is simply no direction that leads out. Even light, trying to turn around and flee, finds that the geometry of space has been pulled out from under it. Cosmic scale does deeply weird magic here. The mass of several entire solar systems vanishes behind a permanent horizon the size of a small suburban town. Starlight that wanders too close bends completely around it. Time itself slows to a crawl near its edge. We use comforting words like whole and horizon to cope with what we are seeing, but what really forms at the end of a star's life is a place where our everyday rules of space and time simply cease to exist. Why should this quiet, cosmic violence matter to you? Because you carry a direct record of this story in your very veins. The iron in your blood is the precise signature of stellar failure. We exist in the lingering afterglow of giant stars collapsing. The torrential neutrino storms, the rebounding shock waves, and the glowing ash scattered from these ancient blasts forge the heavy elements we use to live, breathe, and build our world. So think of that simple iron nail one last time. Feel your own heartbeat. Each steady beat carries out a microscopic trace of a stellar core that long ago ran out of fuel, fell into complete darkness, and in its spectacular falling, lit up the universe with the very ingredients of life. We are incredibly small, yes, but our atoms remember the grandest, most violent endings the cosmos has to offer. And if that profound sense of scale makes you feel something, you are exactly in the right place. If you enjoy these clear, quiet trips to the absolute edges of space, please subscribe and leave a like. There are many more deep dives on black holes, dead suns, and the staggering scale of everything waiting for you right here on the channel. Thank you for taking a moment to look up. Stay curious, and I will see you next time.